Hello everyone, welcome back. Today we are going to solve LeetCode problem 232, implement queue using two stacks. The task is to implement a queue using only two stacks. Queue should support the following operations. Enqueue of X will insert an element onto the queue. Dqueue removes the front element. Peek returns the front element. Empty checks whether the queue is empty. The challenge today is to bridge the gap of the queue and the stack working principle. We need to fully simulate a queue's FIFO behavior supporting enqueue, dqueue, peek, and empty using nothing but two LIFO stacks. Look at the example. Enqueue of 10, 20, 30 makes the queue with elements 10, 20, and 30. A dqueue now removes 10. Again, an enqueue of 40 makes the queue 20, 30, 40. A peek returns 20, the front element of the queue. Again, there is a dqueue which removes 20, the front element. So now the queue becomes 30, 40. Fine. Let us move to the core concept. To understand how to make this work, there is an important core concept to discuss here. We will designate two distinct roles, stack 1 and stack 2. Stack 1 will be used exclusively for inserting new elements and stack 2 will be used exclusively for deleting elements. Done? So stack 1 is used for insertion, stack 2 is used for deletion. Fine. The trick is whenever stack 2 is empty, we need to delete or peek. You will dump all the elements from stack 1 into stack 2 because a stack reverses data. Pouring stack 1 into stack 2 completely flips the order, reverses the order, placing the oldest element, the one that arrived first, right at the top of stack 2. So ready to be processed, right? So this is the important rule. Whenever stack 2 becomes empty, transfer all elements from stack 1 to stack 2. So this reverses the order and you can pop from the stack 2 now. Right. Let us discuss the algorithm for enqueue. The algorithm is very simple, crystal clear. Fine. The rule is very simple. Always push the new element straight into stack 1, our input stack. There is no role for stack 2 here. So what is the algorithm to enqueue? Push the element straight into stack 1. Done. Look at the algorithm for dqueue. Step 1, what happens? You check both stacks are empty. If both stacks are empty, you just print queue underflow. Next, step 2. This is where the magic is happening. Since stack 2 is empty, move all the elements from stack 1 to stack 2. Okay, so after moving the elements from stack 1 to stack 2, now you pop and return the topmost element from stack 2. This is dqueue operation. Done. Let us look into the algorithm for peek operation. So for peek operation also you check if both stacks are empty. If both stacks are empty, what you do? You print queue is empty. Look at step 2 again. You check stack 2 is empty. If stack 2 is empty, move all the elements from stack 1 to stack 2 and return the top element of stack 2. So peek is going to return that. Fine. Done. Look at the algorithm for empty. If stack 1 and stack 2 are empty, return true. Else return false. Direct and simple. Done. So let us discuss the core functions enqueue, dqueue, peek, and empty. So enqueue pushes an element directly into stack 1. Look at the push function. So you need to write the push 1 function for stack 1. So this will directly push the element X onto stack 1. Look at dqueue. Dqueue first checks whether both the stacks are empty to handle the underflow condition. Again, if stack 2 is empty, there is a while loop you see. A while loop continuously pops element from stack 1 and pushes them into stack 2 until stack 1 is completely drained. Fine. Once that is done, once this transfer is verified, dqueue returns the popped top of stack 2. Fine. So you are returning pop2. Done. DQ is done. So let us walk through this example. Look at the NQ operation. Initially, both the stacks are empty. Step number 2, NQ10. 10 is pushed onto stack 1. NQ2, 20. 20 is pushed onto stack 1. NQ30. 30 is pushed onto stack 1. So the logical view of the queue looks like this: 10, 20 followed by 30. Okay, so NQ is done. So NQ, the important role to play is stack 1. There is no role for stack 2. All new elements are inserted into stack 1. Stack 2 is not used during the insert NQ operation. Fine, done. So let us look into an example of DQ operation now. Look at the initial state. Stack 1 contains element 10, 20, 30, where 30 is at the top of the stack. So remove an element from stack 2. If stack 2 is empty, you empty stack 1 contents and transfer the stack 1 contents into stack 2. So look at step 2. 30 is moved to stack 2. Step 3, 20 is moved to stack 2. Step 4, 10 is moved to stack 2. So now pop from stack 2. Okay, so this reverses the order, right? So pop from stack 2. So stack 2 plays a vital role for DQ. Done. So since stack 2 was empty, transfer all elements from stack 1 to stack 2. So in stack 2, the order got reversed. Now the front element is 10. That is on the top of the stack. So you can DQ it. Very easy. Fine. Okay. So now look at the code for peak. Peak also checks whether both the stacks are empty to handle underflow condition. If stack 2 is empty, again there is a while loop, right? So this while loop continuously pops elements from stack 1 and pushes them onto stack 2. So once this is done, peak simply reads the element at stack 2 of top 2 without removing it. Finally, it returns what is called as stack 2 of top 2. Done. So finally, look at empty. This simply returns true if both stack 1 and stack 2 contains 0 elements. Fine. So simple. Okay. So let us analyze the time complexity. So NQ and MT are straightforward order of 1. But you might ask, what about DQ and peak? Don't they have a while loop that takes order of n time while transferring elements? That's a very right question. We have discussed a while loop in DQ and peak. Yes, a single isolated operation can take order of n time. However, notice that each element is moved from stack 1 to stack 2 exactly once during its entire lifetime in the queue. So when you average the cost of that, transferring all operations across, the cost per operation is incredibly small. So therefore the amortized time complexity for both DQ and peak is a highly efficient order of 1. Thank you, and I'm happy to take any questions you have. Happy learning.